Everyone. So welcome to my channel SciZap. So the purpose I started SciZap is to document my journey from being a political science student to delving into the world of technology and building a career there. So I have an arts degree and I went on to work in consulting, and now I'm currently working at a tech company. So from there, I got a few questions, many people reaching out to me on LinkedIn when I started posting videos and short clips, as well as articles, to understand my transition and how I made this journey possible. So the purpose, I guess, of SciZap is to help anyone from arts degree or anyone interested in this field to understand and consolidate their knowledge in the basics of technology and how to ace the interviews, either in consulting or in tech companies. So first, since we are talking about basics, I thought it would be a great idea to really start with the foundations. And the way I started learning about technology is just by doing and understanding basic concepts that everyone talks about. They seem very simple, but to be able to explain them and apply in the day-to-day work is very important for your success. So this video will be dedicated to distributed systems, and I'll be discussing the four most important concepts. So first is scalability, second reliability, third availability, fourth efficiency, and fifth is more optional, I believe. It's manageability. So let's start with scalability versus reliability versus availability. So scalability is the capability of a system or a process or a network to grow and manage increased demand. So any distributed system that can continuously evolve in order to support the growing amount of work is considered to be scalable. So for example, I built an app and I'm the only user, but if you have 10 more users, how will the system function with so many people trying to use it at the same time? So that is what scalability is. So a system might have to scale because of many reasons, like increased data volume, increased amount of work that it has to perform, number of transactions, just like the example that I gave you. So a scalable system would need to achieve scaling without having any performance loss, because we don't want the user experience to suffer throughout our 10 different users who are using this app. So generally, the performance of a system, although designed to be scalable, declines when the system size due to the management or environment cost. For example, network speed may become slower because machines tend to be far apart from one another. More generally, some risks not to be distributed either because of their inherent atomic nature or because of some flaw in the system design. So at some point, such tasks would limit the speed up obtained by a distribution. So the scalable architecture avoids this situation, and what it does is it tries to solve and balance the load of all the participating nodes evenly. So there are two types of scaling available. So one is horizontal scaling, one is vertical scaling. So when you think of these two, the first idea comes back is vertical is stacking, horizontal is laying it out in a big, in a linear line. So for example, horizontal scaling means that you scale by adding more servers into your pool of resources, whereas vertical scaling means that you scale by adding more power, such as CPU, RAM, storage, etc., to an existing server. For example, I have one computer, it's serving one client, and if I need to increase the speed, the first thing that comes into my mind is that I will increase the RAM or the CPU or add more hardware essentially. That is vertical scaling. But with horizontal scaling, it is often easier to scale dynamically by adding more machines into the existing pool. So vertical scaling is limited to the capacity of a single user, and scaling beyond that capacity involves downtime and comes with an upper limit. So I mean, how much RAM and CPU can you add to one computer? And it's expensive too, so it's not the most easily scalable solution. So there are some examples of horizontal scaling, such as Cassandra and MongoDB, as they both provide an easy way to scale horizontally by adding more machines to meet the growing need. So similarly, a good example of vertical scaling is MySQL, as it allows for an easy way to scale vertically by switching from smaller to bigger machines. But this process involves a lot of downtime. So you can think of vertical scaling as stacking up resources. Horizontal scaling is adding more servers, and these servers in today's world tend to be even virtual. So you're not consuming as much monetary cost, and you're saving so much time and spin up costs as well. So now that we understand horizontal versus vertical scaling and what scalability is, let's talk about reliability. So by definition, reliability is the probability a system will a system will fail in a given period. In very simple terms, a distributed system is considered reliable if it keeps delivering its services even when one or several of the software or hardware components fail. So, reliability represents one of the main characteristics of the broader topic of distributed system. Since in such systems, a machine may fail, and it can always be replaced by a healthy one, ensuring that the completion of the requested task. For example, take a large e-commerce store, let's say Amazon, where one of the primary requirement is that any user transaction should never be canceled due to a failure of a machine, and that it is running for every transaction um, that the user ever wants. For instance, if a user has added an item to their shopping cart, the system is expected not to lose it. So a reliable distributed system achieves this through redundancy of both the software components as well as data. So if the server carrying the user's shopping cart fails, another server that has the exact replica of the shopping cart should replace it. So the idea of reliability is that you always have the master-slave replication. So if the master fails, then the slave can take over. And I understand the terminology is not something I accept, but generally in the industry, this is how it's used. So maybe you can consider using this vocabulary, or if you find better terms, do let me know or comment below. So the whole idea of reliability is built around having a master and having a slave. So if the master fails, that the slave can take over. So obviously redundancy has a cost, and reliable system has to pay that to achieve such resilience for services by eliminating every single point of failure. And third, availability. So by definition, availability is the time a system remains operational to perform its required function in a specific period. So it is a simple measure of the percentage of time the system, service, or machine remains operational under normal conditions. So an aircraft that can be flown for many hours a month without much downtime can be said to have a very high availability. And availability takes into account maintainability, repair time, spares, availability, and other logistical considerations. So if an aircraft is down for maintenance, it is considered not available during that time. So reliability versus availability over time, considering the full range of possible real-world conditions that can occur. So that's how I view reliability, that it is available over time. So an aircraft that can make it through any possible weather safety is more reliable than one that has vulnerabilities to possible conditions. So now an interviewer might ask you, explain the difference between reliability and availability. So here goes the answer. So if a system is reliable, it is also available. However, if a system is available, it is not necessarily reliable. So in other words, high reliability contributes to high availability, but it is possible to achieve a high availability even with an unreliable product by minimizing repair time and ensuring that spares are always available when they are needed. So let's take the example of an online retail store that has 99.99% availability for the first 2 years after its launch. However, the system was launched without any information security testing. So the customers are happy with the system, but they don't realize that it isn't very reliable as it is vulnerable to likely risks. So in the third year, the system experiences a series of information security incidents that suddenly results in immediate low availability for extended periods of time. So this results in reputational and financial damage to the customers. So if you are to explain reliability and availability, I would say availability is a subset of reliability, but you cannot say the other way around. So if a system is reliable, it is available, but just because it is available doesn't mean that it is always reliable because you haven't taken care of the faults or the failures that can happen. So the fourth concept is efficiency. To understand how to measure the efficiency of a distributed system, let's assume we have an operation that runs in a distributed manner and delivers a set of items as a result. So two standard measures of its efficiency are the response time, which is known as latency, that denotes a delay to obtain the first item, and second, the throughput or the bandwidth, which denotes a number of items delivered in a given time frame. So the two measures of efficiency are throughput and latency. Latency is how quickly or how slow it responds, and throughput is the bandwidth, the number of items delivered in any given amount of time. So the number of messages globally sent by the nodes of system regardless of the message size, and the size of messages representing the volume of data exchanges. So in the real world example, this is probably how it relates. So latency would be the number of messages globally sent by the nodes of the system, irrespective of the message size. And the second would be the size of the messages representing the volume of data exchanges. So the complexity of operations supported by distributed data structures, searching for a specific key in a distributed index, can be characterized as a function of one of these cost units. Generally speaking, the analysis of a distributed structure in terms of number of messages is oversimplistic. It ignores the impact of many aspects, including the network topology, the network load, and its variation, the possible heterogeneity of software and hardware components involved in data processing and routing. So, however, it is quite difficult to develop a precise cost model that would accurately take into account all of these performance factors. So we have to live with the rough idea of estimation. The last component would be serviceability or manageability. So another important consideration while designing a distributed system is how easy it is to operate and maintain. No one wants a complex system where it becomes very cumbersome over time to maintain and becomes very expensive as a result. So serviceability or manageability is the simplicity and speed with which a system can be repaired or maintained. So if the time to fix a failed system increases, then availability will decrease, of course. And things to consider for manageability are the ease of diagnosing and understanding problems when they occur, ease of making updates or modifications, and how simple the system is to operate. So does it routinely operate within failure or exceptions? So early detection of faults can decrease or avoid system downtime. And one of the best concepts that I have noticed throughout my career is microservices traceability. So as many of the systems are moving from monolith into microservices architecture, which I will discuss in later videos, this concept of manageability and serviceability becomes really important. And I will discuss some of the newer tools that we are currently using to monitor these very vast networks of distributed systems. So for example, some enterprise systems can automatically call a service center without human intervention when the system experiences a system fault. So to summarize and reiterate, there are 5 characteristics that are most important for any distributed system. The first is scalability, second is reliability, third availability, fourth efficiency and manageability, and I guess fifth would be the ease of use for any system. So scalability, again, is the capability of a system, process, or network to grow and manage increased demand. So when you have more users using an app, for example, and the system might have to scale for many reasons, such as data volume, increased amount of work, number of transactions, and those are the most commonly used use cases. There are 2 types of scaling, horizontal versus vertical. Horizontal scaling is adding more servers. Either they can be virtual servers or real servers. Vertical scaling is when you add more CPU, RAM, essentially any hardware to make your computer perform faster. So in today's world, vertical scaling has become a little outdated, whereas horizontal scaling has picked up. Some of the examples would be Cassandra and MongoDB. Again, I'll come back to Cassandra and MongoDB in later videos to discuss more in detail. Second is reliability. Reliability is a probability that a system will fail in any given period, and what are some of the mechanisms we can devise so that our customers don't struggle throughout this. Examples of highly reliable systems are like Amazon, eBay, where the primary requirement is that any user transaction should never be canceled due to a failure of a machine that is running that transaction. So to elaborate, if a user has added an item to their shopping cart, the system is expected not to lose it. So if the system is to be reliable, there has to be a master-slave kind of replication. So if one fails, then something else can take over. And obviously redundancy, it has a cost, and a reliable system has to pay to achieve that kind of resilience for services by eliminating every single point of failure. Now, availability is the time a system maintains operational to perform its required function in a specific period. To recap, reliability versus availability. If a system is reliable, it is certainly available, but if a system is available, it is not necessarily reliable. So in other words, high reliability distributors contribute to high availability, but it is possible to achieve high availability even with unreliable product by minimizing repair time and ensuring that spares are always available when they are needed. Fourth would be efficiency. Efficiency is measured in two ways, one through latency and second through throughput. Latency is how quickly or how slow you receive a response, and throughput would be the bandwidth, which denotes the number of items delivered in a given time. So remember throughput as any per second or per minute, whereas latency is how slow or fast the system functions. And last, serviceability or manageability. It's important to design systems that's very easy to operate and maintain, and are simple enough which has speed with which a system can be repaired or maintained. So if the time to fix a failed system increases, then availability will of course decrease. So things to consider are the ease of diagnosing and understanding problems when they occur. And again, there's a whole chapter that I want to dedicate to services and manageability that ties along with microservices observability in the later videos. So for today, that's everything in terms of distributed systems and the key characteristics. So thank you, and I'll see you in my next video.